Hello, in this last video for chapter 8, or the addition reactions chapter, we're just going to summarize everything that we talked about. So first, let's go over regiochemistry, which again just refers to where something prefers to bond. So where do bonds form? So let's talk about Markovnikov addition versus anti-Markovnikov addition. And we'll just make a little chart of all the different reactions. So let's just start by drawing a reaction of an alkene. And we're going to add, let's see, I'll use different colors. So we're going to add a hydrogen and some other functional group, like a halogen or an alcohol, for instance. So we'll draw that in red, and we'll just label it A. Okay, so we could end up with two different products depending on the reaction that we use. So we could end up with the hydrogen on the side with more hydrogens. Oh, forgot to add a bond here. And then the A, whatever that is, will add to the side that's more substituted. And so that is our Markovnikov addition. Or we could end up with the hydrogen adding to the more substituted side, and the A functional group adding to the less substituted side. And that would be our anti-Markovnikov addition. Okay, so let's say that A is a halogen. Okay, so if A is a halogen, how would we add the halogen to the more substituted side? What type of reaction would we use? So for instance, let's say we're adding HBr across a double bond. What type of reaction is that? Hydrohalogenation. So I'll just put HBr underneath to remind you. Now, how could we add hydrogen and bromine anti-Markovnikov? So what would we need to add to make sure that bromine adds to the less substituted side? Peroxide, right? Just some sort of peroxide. So we're still performing hydrohalogenation, but in addition to our HBr or HCl, whatever we're using, we're also going to add a peroxide. Okay, so what if A is an alcohol? So it's an OH group. How do we add that across the double bond so that the OH group is on the more substituted carbon? What would that reaction be? And feel free to look through your notes. It's always good to kind of think critically about these things, and that also helps you remember which reactions are which. So if we want Markovnikov addition, where the OH group is on the more substituted carbon, we would use acid catalyzed hydration. So remember, we would add something like sulfuric acid or phosphoric acid, so a strong acid, but it is catalytic, so it regenerates in the reaction. And then we'd also add water, which is what's providing our OH group. Okay, now which reaction would we perform to get the anti-Markovnikov addition? Hydroboration oxidation. Okay, so this one's a bit longer. We would need to first add borane tetrahydrofuran, so BH3THF. And then second, we would add a peroxide, hydrogen peroxide in particular, and sodium hydroxide. Okay. Now, last but not least, what if we want to add an alcohol and we want to use Markovnikov addition, so we want OH to end up on the more substituted carbon, but we're trying to avoid rearrangement. So let's just say for that category, we'll say A is still an alcohol, but we want to avoid rearrangement. What reaction would we use? Oxymercuration, demercuration. It's a long name. All right, so again, this one's a little more complex as well. So first, remember, we add that mercury acetate, and it dissociates on its own to form mercury acetate, so a mercuric cation. And then we also have water in there, which provides our alcohol group. And then second, we use sodium, let's see, NaBH4, and that's going to remove the mercury group. So sodium borohydride. Okay. So hopefully this chart helps a little bit with kind of categorizing the different reactions we went over and just sort of helping to remember what is going to produce the Markovnikov addition of our groups versus the anti-Markovnikov positions. All right, so let's go over syn versus anti-addition, because that also can be hard to remember. All right, so this has more to do with stereochemistry than regiochemistry. And again, let's say we have an alkene, and we'll just draw a cis alkene here. And we're adding X and Y across the double bond. So X is in blue, Y is in red. So again, we could have syn addition of these two groups. So we'll just draw them both as wedges, but they could be dashes too, because, you know, either one might occur, as long as they're syn to each other. And let's say we also have the situation where they add anti to each other. So I'll just draw one as a wedge and one as a dash. Okay, so that's our anti situation there, anti-addition. All right, so if, let's say we want to add two alcohol groups across the double bond. So let's say X and Y are both alcohol groups. So what reaction could we do in order to make sure that those alcohol groups are syn to each other? So we would perform syn dihydroxylation. All right, so this one is a little complex as well. So remember, for syn dihydroxylation, we would use that osmium tetroxide, which is toxic. And in the second step, we would use sodium bisulfite or sodium sulfite, either one, and water. Or remember, you could also use potassium permanganate. Oops, I need a capital M there for manganese. So you could use potassium permanganate with sodium hydroxide at cold temperatures. So that's another option too. All right, now what if we want to add the alcohol groups anti to each other? Which reaction would we perform? Anti-dihydroxylation. Okay, now for this one, we would use MCPBA first. And then second, we would use some sort of acid mixed with water. Okay, now what if we want to add bromine across that double bond? Let's see, so let's say that I'm actually going to write this over here. Oh, no, I guess I'll try to squeeze this in. I don't know, we'll see. I might have to change my chart here. It's hard to write on just one slide. Okay, so what if we want to add bromines across the double bonds? Which reaction do we use for that? Halogenation. And is halogenation a syn addition or anti-addition? Anti, because remember, in the halogenation mechanism, we form the bromonium ion. So that kind of blocks one side, and therefore the other bromine has to come in from the opposite side. So that is halogenation, and it's under the anti-addition category. Okay, what if we want to add bromine on one side and OH on the other side of the double bond? So let's say that X is bromine, but Y is an alcohol. Which reaction do we use? The halohydrin reaction. And is that a syn addition or anti-addition reaction? So it's going to be an anti-addition because it's kind of similar to halogenation in that we form a bromonium ion. So the water molecule that comes in next has to come in from the opposite side because again, the whatever side the bromonium ion's on is kind of blocked. All right, and then what if we want to add hydrogens across the double bond? So X is a hydrogen and Y is a hydrogen. Which reaction do we perform? Hydrogenation. So is that syn or anti-addition? Well, it could be both if you use a particular catalyst, the Wilkinson's catalyst that's chiral, but most often it's going to be a syn addition reaction, right? So Wilkinson's catalyst, you could use platinum, palladium, nickel. So we'll just write here hydrogenation, and we use H2 and let's say platinum. Okay. Now, there's one more thing I wanted to summarize, and that is ring opening. So we saw that in a lot of these reactions, we formed a bromonium ion or a mercuric or mercurinium ion, or I forget the name. It was a complex name. So let's see. Oh, this isn't letting me go to the next slide. There we go. So let's just kind of summarize those ring opening reactions. So let's say we've already formed our ring, and I'm just going to use a Z here as a placeholder. So that could be a bromine, it could be the mercury acetate. So let's just kind of write down our options here. We could have chlorine, OH, or the mercury acetate ion. All right, and then let's say one side of this ring has a couple of methyl groups. So this is an asymmetric molecule. And then let's say we add some sort of nucleophile. So that could be a water molecule, it could be another bromine, another chlorine, etc. What side does that nucleophile want to attack? Which side is more stable when it's attacked? The side that's more substituted, because remember those transition states that we drew a couple lectures ago. So if the nucleophile attacks the more substituted side, that carbon does become partially positively charged. So it's kind of like a carbocation. And remember that the more carbon groups that are attached to a positive carbon, the more stable it is. And that's due to, what's that key word? Hyperconjugation. All right, so then we open the ring once the nucleophile attacks. And now the groups are opposite each other. And the nucleophile is on the side that's more substituted. So let's just make a note. The nucleophile prefers to attack the more substituted carbon. Now, I am going to add a little caveat here. This is only if Z has a positive charge. This will come up later, so for now, just know that the nucleophile will attack the more substituted carbon. There's always exceptions in chemistry, right? Okay, so let's actually wrap up the chapter by looking at our Chapter 8 study guide. And this is actually just a chart that you can find in your textbook at the end of Chapter 8. If you have the second edition of the textbook, it's at the end of Chapter 9. So at the end of your addition reactions chapter. And all I've done here is just removed all of the reagents in the middle on the arrows. So the key to this is in your textbook. But this is super useful for trying to remember, how do I get from an alkene to an alcohol? How do I get from an alkene to something with a halogen on it? And you can also make flashcards, kind of using the same method. So for each reaction, just make a flashcard. And on the front, you could put, for instance, halogenation. And on the back, you could put the reagents you would use with maybe an example of halogenation. So let's just go through a few of these. Let's see. So how would we get from our alkene in the center to product number 1? And the X stands for a halogen. How would we get to that product? Well, looking at all of our possible reactions, I would say that we're going to use hydrohalogenation. And we know that that is going to go through Markovnikov addition. So the halogen will end up on the more substituted carbon, which it has here. So I'm just going to write next to the arrow HX, where the X is bromine or chlorine or something. Okay, let's go to product number 2. So here we're adding a bromine to, it looks like the less substituted carbon. So how would we do that? So that is anti-Markovnikov addition. So if we go back to our summary, if we want to end up with a halogen on the less substituted carbon, we would still perform hydrohalogenation, but we just have to add some sort of peroxide to it. So I'm going to write HBr, ROOR. So this is kind of like a puzzle. We're just kind of trying to figure out what's the missing piece here. Okay, so let's go to product 3. So it looks like we're adding an alcohol group to the more substituted carbon. And it looks like there's 2 ways to do that. There's 2 arrows going to that product. Okay, so if I go back to my chart, let's see. Okay, so I want to add an alcohol group, and I want to add it to the more substituted carbon. Okay, so it looks like there's actually a couple different ways we could do that. We could use acid catalyzed hydration or oxymercuration demercuration. Okay, cool. So I'll go back to my chart. And let's see, on the top arrow, I'm going to write the acid catalyzed hydration reagents because on the second arrow, there's a number 1 and a number 2. And I know that oxymercuration demercuration involves 2 steps. So I've got in my first step, mercury acetate and water. And in the second step, we need to remove the mercury group using sodium borohydride. All right. Okay, now for number 4, it looks like I'm adding an alcohol group to the less substituted carbon on the double bond, and we're forming an enantiomer. Okay, so how can we do that? So I'm going to go back to my chart, and let's see, I want to add an alcohol to the less substituted side, so anti-Markovnikov, and it looks like the only way to do that is with hydroboration oxidation. Okay, so in hydroboration oxidation, the first step involves adding borane tetrahydrofuran, BH3THF, followed by hydrogen peroxide and sodium hydroxide. Okay, so let's go to number 5. And if I compare my starting material to my product, it looks like I just added hydrogens. I just got rid of the double bond and made it a single bond. So how do we do that? How do we perform hydrogenation? Well, we need hydrogen, H2, and then you can pick whichever catalyst is your favorite. So I'm just going to pick platinum. Okay, on to number 6. All right, so number 6, we need, let's see, it looks like we're adding 2 bromines, and it looks like they're anti to each other because one is a wedge, one is a dash, and we're also forming the enantiomer. Okay, so if this is anti-addition, I'm going to go to my anti versus syn chart. And okay, it looks like I'm performing a simple halogenation here under the anti category. So I'm just going to put Br2 there. All right, on to number 7. Okay, so here it looks like we're adding OH and Br across the double bond. And the OH group is on the side that is more substituted. Okay, so I'm going to go back to my summary chart for anti versus syn here. Which reaction can I use? The halohydrin reaction. So that adds bromine and OH across the double bond. Okay, so I think you're getting the idea. So you can finish filling out this chart yourself, just kind of using your notes. And again, the key is in the back of chapter 8. But one thing I wanted to do as well is there are a few mechanisms that I would like you to memorize. So the arrow pushing mechanisms, and I'll just circle those. So I would like you to memorize the halohydrin mechanism, the hydrohalogenation mechanism, the acid catalyzed hydration mechanism, and the halogenation mechanism. Now, so I want you to memorize the full arrow pushing mechanisms for those 4 particular reactions. And then you also need to memorize in general all of the reagents here that are needed for each reaction. So definitely make flashcards, kind of go through the examples we went through. That'll help a lot. And I do have a blank version of this reaction map under modules flashcards. Or sorry, modules study guides. So you can print this out as many times as you want, and you can just test your memory on each of these reactions and see if you can remember how to get from the starting material to the different products. Okay, good luck. If you have any questions, you can add them to the discussion board on Canvas for Chapter 8, or you can email me or set up an office hour. All right, so I will see you for Chapter 9.